Hello everybody. In this lesson we're going to focus on the periodic trends. I am going to assume that you learned about these in honors chemistry and that you remember them. Things like the atomic radius, ionization energy, electronegativity, etc. If you don't remember them, I would highly suggest going back to the honors chem tab, finding the lesson where you were taught about periodic trends originally, and going through that kind of from the beginning. This lesson is going to focus a lot on the way we describe and explain these from kind of an AP level perspective. So if you need to refresh your memory of the foundational patterns and reasons, I would go back and look at the honors chem lecture. Now just a reminder that once upon a time we did not have a periodic table. Mendeleev is credited with coming up with what's really close to what we have today. He arranged things based on their properties and their masses, and he left blank spots in his table to account for elements that had not been discovered yet. And he was so good at predicting them, you can see here, he got really close in all sorts of things like mass and density, formulas. He even had very accurate descriptions of what they would visually look like. He didn't get it perfect though. Henry Moseley came along and he's the one who realized it shouldn't be arranged by mass, it should be arranged by atomic number. And that's how we got the periodic table we're used to today. Is our periodic table perfect? No, there's places where the patterns don't work, but our table is very good for most of the chemistry that we do, which is why we use it so much. When you were learning about the periodic trends back in Honors Chem, you probably saw a variety of charts like this, where they showed you the periodic table and they tried to summarize the direction that these trends would increase by. So for example, as you go to the left, your radius gets bigger. As you go down, your radius gets bigger. As you go to the right, your ionization gets bigger, things like that. Now, there's lots of ways to summarize these, lots of different charts you can find online. Everybody tends to have a personal favorite. I honestly don't care which one you like, as long as you find something that works for you. I really like this chart though, because this one is emphasizing the attractive forces between the nucleus and the electron, and in AP Chem we talk a lot about that. So this was kind of the four quadrants of the periodic table. The top right corner tends to have the largest attractive forces because we have a very strong nucleus and a very small diameter, small radius, right? So the nucleus can pull really hard on electrons, and we end up seeing some things as a result of that. The bottom left corner tends to have the lowest attractive forces because it has a very weak nucleus compared to the very large diameter of that atom. And you can see the effect of that low attractive forces. So whichever one you prefer, great, study it, make sure you can answer questions, and you kind of internalize and remember what these trends are. Now, just a couple of things I'd like to point out about the radius before we start talking about the reasoning behind the patterns we see, is that there's lots of ways to measure the atomic radius. If you remember, orbitals are not tangible objects, so we cannot easily measure to the outside edge of an atom because it doesn't really have a tangible edge to measure to. So they come up with creative ways to do this. Sometimes they bond the atom, sometimes they don't. Whatever method they use is going to be slightly different values compared to other ones. That's why when you look up the radius for something online, you may see slightly different numbers because they may be measuring them in different ways. Depends on, what type of experiments they can do, but also the type of atom and what it will behave, how it behaves, which one is easier to do. They do this with lots of different elements, compounds. They take a lot of averaging. You're going to see lots of slightly different numbers. No big deal. It's not like anybody's ever going to ask you on the AP test, what's the radius of bromine? right? They're going to ask you to explain data charts that they give you. They're going to ask you to predict if something might be bigger or smaller, or explain why. A lot of qualitative type things here. Now let's look at the trend for atomic radius. Now, some key things that I want you to keep in mind when you're trying to describe the radius getting bigger going down a group. You cannot just say, because there's more shielding. That's vocab dropping, right? We can't do that. That's not really a reason. That's a vocab term. What AP College Board is looking for is that you understand that the size of the atom is related to the distance the electrons are from the nucleus. And you have to be very specific and mention that the higher energy level is bigger and further away. You can't just say it has a higher energy level, right? We all know what that means. It seems very obvious, but they need you to be very explicit when you're talking about energy level being, higher energy level being further away. So please be very careful about those types of things when you're describing going down a group. Those are key places people make mistakes. So to remind you, as you go down a group, our radius gets bigger. And we want to hear reasonings like this. We want to hear you say things like, moving down a group, you add a principal energy level. You can just say energy level, that's okay too. The larger your energy level, the larger the volume of the orbital, the further the electrons will be from the nucleus, the less attraction you'll have to the nucleus. There will be more shielding, right? Less attraction, larger, further away. All of those things result in the radius being larger. You can't just say because it has more energy levels. That's not good enough. Make sure you are connecting the energy level to the distance, to the attraction, to the shielding. That's why it's bigger. Not just more shielding, not just more energy levels. You see here, bullet points are your friend, right? Don't give me some big giant essay, okay? Some key things about going across a period. You cannot just say, because there's greater effective nuclear charge. That's vocab dropping. We don't do that. Once again, the size is related to the distance. Key thing here is you can't just say, when you go to the right, you add more protons. You have to also mention that you're not going to be increasing the amount of shielding. You have to account for the fact that you are also adding more electrons, but it doesn't matter, effectively doesn't matter, because they're in that same energy level. You also need to be specific and say, because there's greater attraction, it pulls those electrons in closer, therefore a smaller radius. Yes, we understand if they're more attracted, it's going to be closer, but you have to be explicit. You have to show them that you understand that connection. So, we often like to talk about the radius getting smaller, going left to right. So as you go to the right, you add a proton, but you're not adding more shielding because they're in the same energy level. And remember, electrons in the same energy level don't shield very well to each other, right? It's not going to really affect it. If you add a proton with no increased shielding, you're increasing the effective nuclear charge on those valence electrons. So the stronger the attraction is for the nucleus, the stronger your attraction, the closer they are, therefore smaller radius. These are the kinds of bullet points we're looking for when we're going to go through and check off how many points you get, right? We're looking for connecting the dots, not vocab dropping. You got to connect all the dots to baby step us there. One thing that sometimes comes up is the ionic radius. Remember, things in the same group have the same charge. As you go down a column, you're going to end up with a higher valence shell, right? Further from the nucleus, you're larger. You're also going to see things like cations will be smaller than neutral atoms because they've lost that electron, right? And now they're being pulled in closer because the protons can pull on fewer electrons. Your anions will be bigger than the neutral atom because they have an extra electron. There's a little bit more repulsions, so they get a little bit bigger. The nucleus can't pull on one more electron quite as much, right? So it's bigger. And we tend to see the cations are smaller than the anions. One thing we have to remember is that when we have isoelectronic things, meaning they have all the same number of electrons, but they have a different number of protons, we'll see here, the more protons you have, the smaller your radius gets. The protons can pull harder on fewer electrons. You end up with a smaller radius. You might have seen pictures like this. The ones here on the left in red are showing you the neutral atom in gray compared to the cation. When you make cations, depending on how many electrons you lose, you may even drop down an entire energy level. That's a huge difference in size, much smaller. Key thing to pay attention to. And in the right, in the green, you can see the neutral atom is in gray, and then in green you see your anion. They've gained electrons, you can see how much bigger they are. Next, you should probably remember ionization energy, right? The amount of energy required to remove an electron from an atom. We do this when it's in a gas state. And one key thing to always remember is that it takes energy for this to happen. The electrons are not just going to leave on their own. They do have to have a little bit of energy to remove them, right? The ones on the outside are the easiest to remove, right? They have the lowest nuclear attraction. You may sometimes see people represent this in a very generic way, like that, where you have an atom, you put in a little bit of energy, you can remove the electron. The second ionization energy would be to take that ion and remove an electron from it. So now instead of a +1, you have a +2. We call that a subsequent ionization. Now, people tend to make fewer mistakes on all the other patterns compared to radius. Radius is the one where they mess up a lot. But we do want to still be careful with our reasonings for ionization energy. You can't just say, more effective nuclear charge. You have to give a full bullet point, connect all the dots type of an answer. So each time you go to the right, you add a proton. You don't have more shielding because you're adding electrons to the same energy level and they don't shield as well, which is increased nuclear attraction, which makes it harder to take one away, which yields an increased ionization energy. You should start to feel like your reasonings are repetitive. If you really understand the atomic radius reasoning, these ones will come very easy to you, I find. They're all connected because if you remember from our previous lesson, everything is about attractions and repulsions. Thinking about it going down a group, each time you go down a group, you have another energy level, you have more shielding, increased radius, lower attraction, so it's easier to take an electron away, so you have a lower ionization energy. Now, you may stumble across some questions where they're going to give you some data that seems inconsistent with our pattern. They will show you an exception, an irregularity, and they'll ask you to brainstorm a reason why this might be happening. You should always be telling yourself, this must be because of attractions or repulsions. So for example, they may give you an irregularity related to how full is an orbital. If you imagine your orbital diagram, they're asking you to see if you remember and can figure out things like when you pair up an electron, you will now have a little bit extra repulsion there. That would make it easier to remove an electron, which would explain an ionization energy lower than you might expect. They may give you an irregularity when you're transitioning to a new shape of an orbital, like when you're going from magnesium to aluminum. And what they're asking you here is, do you remember that the p orbital does not penetrate as much as the s orbital? So therefore, aluminum actually has less nuclear attraction and a lower ionization energy than expected, because that p orbital is not helping out as much as it should. You might have seen graphs like this. You may have to identify which things are the noble gases, for example. Well, those should be the ones that have the highest ionizations, right? You can see areas here where there's not much changing. Well, those are the transition metals. Very little changing across there as you fill those d orbitals. You might have seen pictures like this, kind of representing it in 3D. Whatever's helpful to you, focus on that. I really like charts like this when we're trying to look at those subsequent ionizations. That's when it's not the first ionization energy, but it's the second or the third or the fourth. I think they really help us visualize what's happening as we keep removing electrons. You should notice it takes some energy to take the first one away. Always takes a little bit. But each time you take an electron away, it's going to get smaller because you have a greater nuclear attraction, right? So it makes it a little bit harder to take the next electron. That's why we see an increase in ionization energy for each subsequent removal. Now, if you notice, there are places where we see large jumps. See these boundaries between the blue and the pink here? When we have sodium, first ionization is pretty low, second one's huge, right? Because when we take that first electron away, we've dropped down to the lower energy level, and now we have a much smaller atom. And so trying to take the next electron away gets very difficult. You cannot just say, it doesn't want to lose more because it looks like a noble gas now. They like being noble gases, right? We're not personifying that, okay? Don't personify your atoms like that. It's that it's a smaller atom, so it's harder to take an electron away because the nuclear attraction is so much larger, because the atom got so much smaller. You can see for magnesium, the first one is okay. Second one's harder because it's smaller, but it's not terrible. And then there's a huge jump because Mg2 plus has dropped down to that lower energy level. So now it's a much, much, much smaller ion. You don't want to try to take that third one because it's going to be really, really tough. You can see, look at that huge jump. Aluminum, that jump comes after the third ionization. The fourth one's going to be really tough. What this can help you do, looking at a chart like this, is to figure out what the most likely charge on the element is going to be. That can help you identify an unknown element. The charge is going to be whatever the number of ionizations was before that large jump. So they'll sometimes give you data like this and ask you to explain which element it must be. Electron affinity doesn't come up as often. I just want to cover it a little bit just in case it does. The electron affinity is the change in energy when the neutral atom gains an electron. So it's kind of the opposite of ionization in a way. It's measured in the gas state. Usually energy is released. Usually this is an exothermic process. Not always, okay? Some of the alkali metals, the noble gases, those really don't want to be gaining an electron, do they? So those end up having endothermic values. It's not favorable for them to be gaining electrons. The more energy that's released, the larger the electron affinity. And that's where people get kind of tripped up here. The larger your negative number, the larger your electron affinity was. So be a little bit careful because of that negative sign. It gets a little bit hard to talk about. Usually as you go down, you'll see a decrease. Not everything does that. One of the things that you're going to see going across is that it gets more negative, but it's not very perfect. One of the reasons they don't talk about electron affinity very much is because there's just so many exceptions. Some of them you can explain easily, like, oh, you have to pair the electrons, so that's not as good, right? So it's a lower electron affinity than you'd expect. Sometimes you'd have to be going to a higher energy level, right? That's not as good, lower than you'd expect. Halogens have the highest. Remember, those things are desperate to get electrons. This would just, I would not stress out too much about how these patterns for affinity don't work very well. You can see huge variations. As long as you kind of understand the concept of electron affinity and you could explain values that were given to you, you should be fine. But it's one of the lesser used trends. Electronegativity, that's one you should be familiar with. The ability of an atom to attract the electrons within a bond. We see it get larger as you go to the right, gets lower as you go down a group. I always told my students in Honors Chem to think about fluorine and francium. Those are kind of the corners that help you remember your trends. It's important that you remember that noble gases won't even be given a value typically. We consider them to have the lowest electronegativity because they are not going to be attracting electrons. And it's opposite of the atomic size trend, right? One thing that we'll get into a bit more in AP Chem compared to Honors Chem is the difference in electronegativity between atoms. So the larger your difference, the more polar the bond is that you have. And that will come into play when we're starting to talk about Vesper and polarity, right? We can end up with a situation where one side of your molecule or one side of your bond has slightly more negative charge than the other because the electrons are being pulled in that direction and they will spend more time occupying that side. We say there's a higher electron density over there, gives it a slight negative charge or negative end to the molecule. That can affect the properties. Sometimes, right, you might see different charts and things. Now, sometimes you might be asked to mathematically calculate how polar a bond is or how not polar a bond is by doing a subtraction of the electronegativity values. You would probably be given a chart and the actual data to use. Not everybody agrees on what the cutoff points should be. We should understand that if you have two of the exact same atom, the electronegativity difference would be 0. They'd be perfectly sharing. There's no, negative end of the molecule there. There's no difference. Sometimes there might be a tiny difference. It's not enough to really matter. It's not enough to really change the properties significantly. Compared to something that's polar, where the electrons are still being shared, but the electronegativity difference is large enough that it can have an impact on its behavior, on its properties. And if the electronegativity difference is large enough, then you could end up with an ionic compound instead, where they're not really even sharing anymore. It's been completely transferred. Where these cutoff points are is disputed. Some charts you might see 1.7. I've even seen like 1.4. Honestly, just use the chart that you're given. Don't worry about memorizing it or anything like that. I love this picture because I like how they show here purely covalent. All the electron density is shared equally. Compared to over here, the left side is hogging the electrons, isn't it? It's more electronegative and it's drawing the electrons this direction. It results in a slight negative charge and a slight positive charge, partial negative, partial positive. And if it keeps going, then this one on the left completely took the electron and now it's ionic. Some examples like Cl2, right? Two identical atoms bonded, totally covalent, compared to something that's very polar but not quite enough to be ionic. Sodium chloride, our classic ionic example. If we end up with one side of the molecule having a partial positive versus partial negative, we say it has a dipole. We can measure the strength of that difference, and the directions that they all point, come up with something called a dipole moment. The size of the partial charges and the distance between them is how they come up with the strength. I'm not going to ask you to do a calculation with this, but you can see here that the size of the charge and the distance, the radius, right, between them, that all ends up contributing to how strong that dipole moment is. When we're talking about whether or not a molecule is polar, we see if all of these various dipole moments cancel each other out by pointing in opposite directions, or if they're additive and you end up with one side of the molecule being partial negative, partial positive. So this idea of the difference in electronegativities resulting in unequal sharing of electrons, that will come back when we start looking at our three-dimensional shapes and our polarity. The last thing on this lesson feels quite random, and to be honest, it is a little bit, but since we are talking about atomic structure, and this has to do with arrangements of electrons, it's kind of the best place I could think of to put it. But it has to do with magnetic properties. And so if you have something called paramagnetic, that's an atom, or I guess an ion too, right? Where you have unpaired electrons in the orbitals. And that will result in the material being slightly attracted to a magnetic field. Compare that to what we call diamagnetic, where all of your electrons are paired up in their orbitals, and that results in no attraction to that magnetic field. In fact, it's slightly repelled. There are some things called ferromagnetic, which is when we have a lattice structure, like a crystal, that keeps its magnetism even if you don't apply a magnetic field to it. So sometimes these terms will come up when they're trying to talk about the arrangements of electrons inside their orbitals. In college chemistry, this becomes quite important because we use these magnetic properties to help us figure out the structure of some of the molecules using something called an NMR machine. Big giant magnet that you put your material inside of. And you turn the magnet on, generate that magnetic field, you turn it off, you see what the electrons do, and you can process the data and figure out the structure of your molecule. They use that in MRI machines too. It's the same concept. So in an NMR machine, you get something like this, where you get these peaks that correspond to certain hydrogens on your molecule, and their placement on the graph and how many peaks you see and the height of the peaks tells you structural information. When you have an MRI machine, they process all of that and they turn it into pictures of the body, right? Which is really, really cool. So what they're doing is you have all of your atoms and their individual magnetic fields moving around. You turn on the machine and it lines them all up. You send like a burst of a radio frequency to kind of get things to spin certain directions. You turn it off and you see how the atoms respond, and if they return to their normal positions, what energy do they give off when they do that? And that's how they can use the computer to process and give you your images. Okay. All right, everybody. I know that was a pretty long lecture, but I hope that it's helpful to try to show you the level of detail we're looking for in our periodic trend explanations at the AP Chem level. And remember, we're not going to vocab drop, but instead we're going to explain how the attractions and repulsions between the nucleus and electrons all come together to explain the patterns that we see. All right, everybody, that was it. I hope that was helpful. Bye.